The cheat, the cheat. Who's the guy who listens to the beat? The cheat. Okay, so what we're talking about here is critical mass for a modern physics for like a nuclear reactor. Okay, what we originally had, and we saw this in our last video, is that if we take a neutron and we hit something like uranium 238, then, or 235, excuse me, 235. Then we're going to get uranium 236 out of it, but only for a small period of time. And then we're going to get two different products out of there, and normally we get 3 neutrons. Okay? Now, if you have enough stuff, what I mean by stuff is enough of this initial element here, this uranium 235, then what can happen is these 3 neutrons initially, they can branch out and strike other pieces of uranium. So we get 1 neutron coming in, and it gives us 3 neutrons. And each of these 3 neutrons could give us 3 neutrons on their own interactions. Uh-oh, if you see where this is going, you can see this is going to be a mess really quick, because each of these could give us 3 more, and oh boy, this is too many things. This starts to just run away. Okay, in fact, we call this like a runaway meltdown. But we get a chain reaction going because we're getting more neutrons out than what we put in, and if we have enough mass in this system, this could be self-sustaining. This is what we use for nuclear reactors. Our first nuclear reactor was made in around 1942 by Enrico Fermi. It was done at University of Chicago, and I believe they put it either underneath the tennis courts or the football field. They really wanted to put it away from everything, so in case something bad happened, they could just kind of shut it all down and kind of dump the fields on top of it, and just keep this thing enclosed for all eternity if they had some issue. But they didn't, and we had our first sustained nuclear reactor. Now, there are some issues to overcome with this reaction here and these 3 neutrons. If these 3 neutrons are all interacting with another piece of uranium or another atom of uranium, then you're going to quickly get a ton of energy being kicked out here, and you're going to burn through your entire reaction, and you're going to get a runaway effect. Okay, you're going to essentially have a meltdown here. What we need to do is we need to ensure that some of these neutrons keep the reaction going, but some of them do not. Because what we kind of want here is this has struck 1 uranium, and it would be very nice if we kept this reaction going just 1 to 1. So 2 out of the 3 neutrons coming out might miss, and we only get 1, and we only get 1, and we only get 1, and we only get 1. This is very nice. This is nice and manageable. We can control this reaction moving forward. We want all of the extra bits out here, every other neutron, we want them to kind of miss. This is a really difficult thing to do, and to do so, we actually need to set up a little bit of a system here. What Fermi recognized in this reaction is, in order to get this to work properly, this neutron out in front really needs to be slow moving. And this is a bit of an issue because all the neutrons that got kicked out, these are all fast-moving neutrons. So we need these neutrons to slow down, and we need some of them to just miss or go away somehow. And here's how you do it. You think about the probability of the absorption. When we think about the probability of a neutron being absorbed by that nucleus to make uranium-236 so that we can get the decay off of it, we know that it's only going to happen for this slow neutron reaction here, okay? Now, to do this and to get a good reaction, we need a nice elastic collision. And we know there's no such thing as a perfectly elastic collision, but when we think about atomic particles striking each other, we can kind of simplify things in that way. And the best way to do this is if you can hit something with its own mass or a slightly different mass, then you might be able to slow down this neutron. And what you do here for these many elastic collisions is you implement a moderator. This moderator is some substance that you put around your uranium or your reaction material here, and its entire purpose is to have things bump into it. As these neutrons bump into it, these neutrons could be lighter than whatever is being the moderator here, and that means on these collisions, those neutrons can slow down. In some of these cases, too, that moderator will actually act and completely stop the neutron or kind of absorb it in a way, such that we don't have to worry about that neutron anymore. Now, there are a few different types of moderators that we can use. The two common ones are just water, but there's two types of water, and I know that sounds weird, but there's water with traditional hydrogen. This is what we call light water, because if you do H2O with this, you only have the one proton in each of your hydrogens here. So we call this a light water setup. The other option that we can have is a heavy water setup. And I know that sounds weird, but it's hydrogen with a neutron in the nucleus as well. This is still just H2O, but we have two more neutrons here, so it's heavy water. These two different moderators here, they require slightly different enrichments of uranium, and because of that, one of them is more enriched uranium than the other one. It actually goes all the way up to like weapons grade uranium, which is how you make atomic bombs, or what you need for atomic bombs. And as a result, the U.S. doesn't like to use some of these types of reactors because it requires you to recycle the material and to kind of upgrade it, and there is fears about nuclear proliferation whenever that happens. So two different waters here using as moderators. Canada actually uses the heavy water setup. They're called CANDU reactors. CAN being Canada and DU being deuterium, because that's what this the hydrogen with an extra neutron in there is called. It's called deuterium there. Okay. Now, one moderator that is also used, you can have a graphene moderator, which is actually just carbon. You could use carbon or a graphene in order to moderate. And there are all sorts of like interesting reactors you can set up with this. It works as a nice moderator here. There are some reactors that are like salt-based reactors, and they kind of do like kind of weird stuff. But in every single case with these reactors, what is occurring here is that you are getting neutrons to interact with that uranium to facilitate further reactions and to keep chaining and chaining and chaining. Okay. But in order to do this, we have this equation up here with uranium-235, and that does mean that you need to enrich your uranium. If we look at uranium, most of the uranium out there is actually 238 and uranium-239. That comprises, well, I think 238 is something like 99% of all the uranium is uranium-238. We would need to get all this stuff down to 235, which is the enrichment of it. And that does require some nuclear proliferation, or rather, you can have that issue arise because now you have weapons grade material. So kind of a somewhat dangerous thing. But in terms of just the reactors themselves, they're actually very straightforward and generally very safe, with a few exceptions through history. Now, the other way that you can actually get these neutrons to kind of dodge out of the system is to actually just have them miss. Some of these neutrons in the system, they're actually going to escape. If you think about, you have a uranium rod and you put it in a moderator, so you put it in some water or some graphene, it can be the case where some of these neutrons just get out. They have completely escaped, which means that some of these neutrons we don't even have to worry about. They're going to miss the other pieces of the uranium, all the other molecules, and they're also going to miss the moderator and get out. So some of these things we don't have to worry about. We're not going to have a perfect one-to-one like we kind of drew initially up here. Some of these will miss. They'll misfire essentially, but the moderator really helps us keep all this in line. Okay, and in order to get this reaction going so it is self-sustaining, you need what is known as a critical mass. Generally speaking, it's a few kilograms for most things. If you've got about like 10 kilograms of most radioactive substances, you can get close to a critical mass. And because of this, you could easily have a briefcase with a critical mass of some substance in it. This is a very dangerous thing because back in the 40s, and if you want to look into this history, like it's all over YouTube, but there were a number of criticality incidents, especially at Los Alamos, where they were running tests in the 40s on figuring out as a bombs and an arms race going on, what we could do with this, how it would work, and in one incident, they had two subcritical masses that were close together, and they were actually just separated by a screwdriver. And then the screwdriver slipped, the masses touched, and you instantly had a critical mass and a chain reaction, a runaway chain reaction like this. The person that was immediately running that experiment suffered immediate radiation poisoning and died within about 5 days. The other few people in that lab were badly injured from this. They had a lot of radiation sickness and some lasting effects from that. So just a few kilograms of this stuff is enough to just touch them together. Boom! You get a nice reaction, and it's kind of dangerous. Now, in terms of how we keep these reactions in check with these moderators, what these uranium rods in the power plants are actually hooked up to our control rod system that can bring them up or down, so either into the moderator or out of the moderator to kind of change the rates at which this reaction is happening. And we call this here a multiplication factor. We're really looking for just one neutron to trigger one neutron and keep it going. So if we are in a perfect world, then this factor, which we call F, is perfectly equal to 1. But in order to keep our reactor going, this needs to be greater than or equal to 1. In a perfect world, it is 1, but it can be greater. We're starting to get like runaway effects, so we put the control rod down further into the moderator. We slow the reaction down, and then when it slows down, we bring it back up, bring it down, bring it up, bring it down. You get the idea. If you have a reaction that is less than 1, we call this subcritical. And if your multiplication factor is just greater than 1, it's just scoring, we call this a supercritical. And this is where you lose control. Okay? So we really, really, really want to keep this multiplication factor just pretty much at 1 for our power plants. It's when we can't control these rods going up and down that we start to lose control. And in Fukushima in 2008, one of the issues that they had there for a brief period of time was they lost electricity to their power plant, which meant that they couldn't control these rods going up and down. A lot of the power plants being built now have powerless fail-safes, and one of the things that, if you're building a power plant that you'd be nice to have is a water tower, or possibly build your reactor at the bottom of a valley next to like a lake. And if something goes wrong with your reactor, you just need to flood the entire plant, because then you'll put these control rods underneath lots of water, which is an excellent moderator for them. And as a result, you'll keep the surrounding environment very safe. Water is actually such a great moderator that if you had a swimming pool and you put one of these control rods at the bottom of it, like a 12-foot deep swimming pool, you would be fine, like just walking around that pool. I think about like 15, maybe 18 feet deep. You could swim at the surface of the pool and not have any issues. It's actually more dangerous to be standing out of the pool and just be underneath the sun. You'd get more radiation that way. So water is an excellent moderator here. There's a whole XKCD thing about that if you're curious. But this is just some general ideas about critical masses that you might need, and then what we're doing in our power plants in order to kind of get these reactions and how to keep them going. But no matter what, once you get these reactions going, you are really just trying to heat up water into steam. That steam you'll use to turn a turbine, and as we saw back in electromagnetism, when you turn that turbine, you can use induction to create a current. So we're really just heating up steam here, and we're just doing that, releasing energy off of these uranium rods. So nothing too wild and crazy here. with that, this is finished. In our last few videos here, we'll be taking a look at some example problems regarding some possibilities of calculations pushing forward or not happening, some binding energy things, and will reaction goes. But until next time, adios, and you all take it easy.